Alright, calm. AQA A level chemistry topic 6 patterned, yeah? Completely patterned. We're gonna get through this, yeah? Dynamic equilibrium. So reversible reaction will reach dynamic equilibrium, yeah? This is when the forward and backward rate of reaction is the same and remains at a constant rate, yeah? So when the forward rate of reaction is the same as the backward rate of reaction, and it doesn't change, so the backward reaction doesn't change, and the forward reaction, the rate doesn't change, yeah? It's constant, yeah? Then it will reach dynamic equilibrium. Dynamic equilibrium, yeah, can only occur in the closed systems, yeah? Because, like, it can't go anywhere, innit? Calm. So yeah, so what does this mean? Yeah, well, it will ask you, yeah, what's the two conditions for dynamic equilibrium, and that's what you can state, yeah, that the backward and forward reaction has to be same rate, and it has to say constant rate, yeah, dynamic because it can shift to forward and backward, yeah. Alright, calm. Le Chatelain principle. When a system is subject to change, the system will alter to affect effect of the change, yeah, to lessen the effect of the change, yeah. So when you do something to the system will counteract you in order to reduce what you did. Yeah. So whatever you did to the system will do opposite to you. So changing temperature. Increase in temperature favors the endothermic reaction. Because if you increase the temperature, you're increasing the heat. Yeah. So what it's gonna do is it's gonna want to decrease the heat. Yeah. It's gonna want to calm it down, cool it down. You know what I'm saying? So go to the endothermic direction because endothermic uses up energy. It uses the energy that you put in. That excess energy is gonna be used and it's gonna decrease the temperature overall of the system. Yeah. Because endothermic makes it colder. Yeah. Decreasing the temperature does the opposite. It's going to favor the exothermic side, yeah? So that means that it's going to produce heat now to go against you. You made it colder, it's going to heat it up again. The system's going to go against you and heat it up. It's going to go to the exothermic side, yeah? Now, to know which side is exothermic and endothermic, yeah, above the arrow, below the arrow, yeah, you'll see delta H, yeah? It will either be negative or positive. If it's positive, that's endothermic. That means that's the endothermic direction. If it's negative, then it's the exothermic direction. And if one side is exothermic, the other side is endothermic. Change in pressure, yeah. So increase it so deep. If I've got a container, yeah, and it's got bare moles inside, and I've got another container and it's got less moles, yeah. Which container has more pressure? The one with more moles in it. So therefore, what I can say, yeah, is that when I increase the pressure, it will favor the side with fewer moles. Because if I increase the pressure, it's gonna try and reduce the pressure. So it's not gonna go to the side where there's bare moles, is it? It's gonna go to the side where there's less moles to decrease the pressure. Do you see? Decreasing the pressure favors the side of the reaction with more moles. So if you decrease the pressure, it's going to want to go to the side with more pressure. So the side with more moles, yeah? Changing concentration. Increasing the concentration of reactants here will favor the side that produces products. If you increase the concentration of reactants, there's now excess reactants here. You want to use it up. So it's going to go to the products. Do you see that? Yeah, it's going to be used to go to the products. Decreasing the concentration of reactants here will favor the reaction that reforms the reactants. So if you decrease the concentration of reactants here, you're going to want to make more reactants now. It's going to want to do the opposite of you, yeah? So it's going to want to increase the reactants. So it's going to go to the side that makes reactants, yeah? Easy. Equilibrium constant, yeah? An equilibrium constant greater than 1 indicates that forward reaction dominates. This works at a certain temperature, yeah? So this changes per temperature. But at a certain temperature, if the temperature is constant, yeah? You have something called an equilibrium constant. This is like a ratio of product to reactant, of how much product is formed by reactant, yeah? So, what do I mean by this? What do I mean by this, yeah? If I got a reaction, small a, big A. Small b, capital B. Small c, capital C. D, capital D. Yeah? This could be 2a plus 3b gives me 4c plus 5d, let's say, yeah? What happens is you put c times d, the products, times each other, divided by the reactants, times each other. The square bracket means concentration. So you do concentration of c times concentration of d, divided by concentration of a times concentration of b, yeah? And what you do is the number in front, so the moles, yeah? So like if it's 2a plus 3b, yeah? The 2 becomes a power, so it becomes a to the power of 2. B to the power of 3. You see, yeah? So big A to the power of small a. Big B to the power of small b, yeah? So that's how this works. Calm. The units can change, yeah? So let's say I've got A times B over C, yeah? What's going to happen here is the concentration is measured in mole per dm cubed, yeah? So mole per dm cubed times mole per dm cubed over mole per dm cubed. Mole per dm cubed and mole per dm cubed are going to cancel out, yeah? They're going to cancel out because you got mole per dm cube here, yeah? So it can divide, it can cancel, yeah? And hence you're going to be left with mole per dm cubed as the unit, yeah? Because that's left there. However, yeah, if this was there was also a d down here, yeah, and it was ab over cd, then it would be mole per dm cubed over mole per dm cubed, mole per dm cube, yeah. And as a result, everything would cancel out. Mole per dm cubed would cancel mole per dm cubed. Mole per dm cubed would cancel mole per dm cubed. You get that? So then the unit would just be 0 for Kc, yeah? So you also need to find a unit whenever you find Kc. Alright, calm. Reaction of bromine gas with chlorine gas, yeah? So this is another thing that people don't show you, yeah? This is an ice diagram, ice table, yeah? So make sure you know about this as well, yeah? It's easy. This is a bit of a harder question, yeah? But normally it's easier than that. Calm. So, a reaction of bromine gas, whatever, initial concentration of that, 0.2, big M means mole per dm cubed, by the way, molar, yeah? But with no initial concentration of Br2, Cl, that would mean the equilibrium concentration of that, yeah? So let's do this in easy. What you do is you write the reaction first, yeah? So Br2, Cl2, and 2BrCl. Calm. Now what you want to do, yeah, is you want to write ice. Write ice, yeah? Initial, change, end, yeah? 0.200 is the initial. 0.200 is the initial Cl and Br2, yeah? Because that's the initial concentration of the two reactants, it says, yeah? So you write that down as initial, yeah? Now, product. You might be thinking, what's the product? How much product concentration? Well, deep it, bro. The reaction hasn't happened yet. We're talking about at the start. So how could you have produced anything? So it's 0. Does that make sense? Always 0, yeah? Calm. Now, sometimes it will tell you what the end concentration is, and based on that, you can find the change, and then you can just divide the change by 2 over here. But here you don't know, it's a bit of a harder question, yeah? So what you need to do here is just assume it's X, yeah? Deep it. If a reaction happens here, I'm going to use the reactant, isn't it? So the reactant is going to lose concentration, it's going to lose minus X. So the change for Br2 is going to be minus X, yeah? And at the end, it's going to be 0.200 minus X, yeah? Calm. Same for Cl2. I'm going to use X. You can just call X any number, yeah? 0.200 minus X is going to be 0.200 minus X, yeah? Now, if I used 1x from Br2 and I use 1x from CO2, how much product is this going to gain? It's not going to lose. We're making product here, yeah? How much is it going to gain? It's going to gain 2x now, yeah? Another way to do this is Br2 and Cl are 1-to-1 ratio, but 2Cl is 2 ratio, so you have to times by 2, yeah? And hence 0 plus 2x is going to give me 2x at the end, yeah? Now just make the equation. I've got make the equation for Kc, yeah? Kc is going to equal BrCl to the power of 2, because the 2 goes up, the moles here, as a power, divided by Br2 times CO2. So Kc is equal to BrCl to the power of 2 over Br2 times CO2, the concentrations here. Now just substitute the numbers in. The concentration for BrCl was 2x. Concentration for Cl2 and Br2 was 0.200 minus x, so I combined them. I just times them and made it squared, yeah? And then the Kc it told you was 7.20, yeah? So now what you can do is just square root both sides here. You get this square root of 7.20 equals 2x over 0.200 minus x, yeah? And I'll just times this up and then sort everything in it, pattern everything here, yeah? Just find x, that's easy GCSE type maths, yeah? And that's the end of it, man. Easy. Easy question, yeah? Don't let this get you.